Hello and welcome to this presentation on logarithms. This presentation assumes you have seen two previous presentations, one on the definition of a logarithm and one on the laws of logarithms, both of which we'll be using in this work. Definition of a logarithm here. If we have an expression y is equal to b to the x, using the definition of a logarithm, we can write that as x is equal to log to the base b of y. The left-hand side expression is denoted as exponential form and the right hand side as logarithmic form, where in this case b is the base of the logarithm, y is a number and x is the exponent or the logarithm. In the questions that follow we'll be finding the value of x in most of the cases. Just a brief review of the laws of logarithms here. There are three laws of logarithms, but it's primarily the third law we'll be using in this set of notes. We're looking at the log a to the n format and writing it as n log of a. I'm going to take you through some examples now on solving what are called indicial equations using the laws of logarithms. In example 7, we're asked to solve 3x is equal to 5. We've got to find the value of x using logarithms. And this is one of the main advantages of logarithms. It allows us to solve for powers, in this case x. So 3x is equal to 5 from the question. What I'm going to do first of all is take logarithms of both sides of the equation. So on the left hand side I get log of 3x is equal to on the right hand side log of 5. I'm now placing myself into log domain where the laws of logs can be applied. So I'm applying the third law of logarithms here to the left hand side of the equation. So I've got log a to the n, log 3 to the x. In the previous line, I now write that as n times the log of a, so x times the log of 3 in this case. That's equal to the log of 5, so simply rearranging the equation, x is equal to log of 5 divided by log of 3, which gives us 1.465, 3 decimal places. You can always check the values of x by putting them back into the original equation, and if we have 3 to the power of 1.465, we get 5. So it checks. Example 8, we're asked to solve 4 to the power of x minus 2 is equal to 6. So again, writing down my equation given to us, 4 to the power of x minus 2 equals to 6, I take logarithms of both sides of the equation. So on the left hand side, log of 4 to the power of x minus 2 is equal to log of 6. I again apply my third law of logarithms to the left hand side, so from my log a to the n format I go to n log of a. I've got x minus 2 times the log of 4 here. Notice the x minus 2 in the bracket. It must be placed in the bracket to keep our BODMAS correct here. On the right hand side I have log of 6. Simply rearranging the equation, dividing both sides by log of 4, so x minus 2 is equal to log of 6 divided by log of 4, and then simply adding 2 to both sides, I get the value of x, which is 3.29. Okay, example 9 here. Slightly different question to the previous examples. We're asked to solve 55.6 is equal to x to the power of 2.7. So in this question we're not trying to find the index, we know it's 2.7, we're trying to find the number x that's raised to that index. So 55.6 is equal to x of 2.7. As before, I take logarithms of both sides of the equation, so log of 55.6 is equal to log of x of 2.7. I apply my third law of logarithms to the right hand side of the equation, so I get 2.7 times log of x. So I've gone from log a to the n on the previous line to n log of a, 2.7 times the log of x. In this particular question I need to rearrange the equation to find log of x, because x in this question is associated with the log function. So in this case, dividing both sides by 2.7, I get log of x is equal to log of 55.6 divided by 2.7. And all I've done on the next line is evaluate the right hand side. So log of x is equal to 0.6463. I'm now going to use the definition of a logarithm to find the value of x. From previous work, log to the base b of y is equal to x. That was the logarithmic form in the definition. We can write that as y is equal to b to the x. That's the exponential form. So if I take anti-logs of both sides, which is often a term used, I'm basically applying the definition of a logarithm. I'm going back from my log domain into the real world, if you like, trying to find the final value of x. So in this particular case, I've got log to the base 10, we're using base 10s here, common logarithms, of x is equal to 0.6463. So in this case, the b is equal to 10, the y is equal to x, notice, and the x is equal to 0.6463. So writing that in my exponential form, my y is now x is equal to the base 10 raised to the power of 0.6463. Doing the numbers on that, I get x is equal to 4.429. So if you don't follow the application of definition there, don't worry too much, because all you need to do on your calculator is use the shift and log function of the 0.6463 and it will give you 4.429. Example 10, a descriptive question. If £12,000 is invested at an annual compound interest of 3.5%, in what year would the investment be worth £24,000? In other words, have doubled. The compound interest formula is given to us as nn is equal to a times r to the power of n minus 1, where nn is the value after n years of investment. A is the initial investment, and r is called the common ratio, and r is 1 plus the interest rate. So from the question, nn is equal to a times r to the n minus 1, where a in this case is £12,000, nn is £24,000, and the common ratio r is 1 plus 3.5%. Don't forget percentage is written as 0.035 here, divided by 100, so the r value is 1.035. So on the left hand side of my equation, nn is 24,000, 24 times 10 to the 3, and that's equal to, on the right hand side, 12,000, 12 times 10 to the 3, times by r to the power of n, 1.035 power n. All I'm doing on the next line is simplifying both sides. I'm dividing both sides by 12,000, so I get 2 on the left hand side and 1.035 to the power n on the right hand side, just to simplify the numbers. If I take logs of both sides of the equation, I get log of 2 on the left is equal to log of 1.035 to the power n on the right. If I apply my third law of logarithms on the right hand side, I get n times by the log of 1.035. So I've gone from log a to the n on the previous line to n times log of a, n times log of 1.035. Simply rearranging now, n is equal to log of 2 divided by log of 1.035. That gives me a value of n is equal to 20.1. So 21 years. Okay, exercise 1i here. We're going to solve some more problems based on the examples on the previous slide. So in part 1 here, x to the power of 5.4 is equal to 64.5. We've got to find x. So again, taking logs of both sides of the equation, we get log of x to the power of 5.4 is equal to log 64.5. Apply my third law of logarithms here to the left hand side. I go from the log a to the n format to the n times the log of a, log of x in this case. So 5.4 times the log of x is equal to the log of 64.5. Simply rearranging the equation to find log of x, make it the subject of the equation, I divide both sides by 5.4. So log of x is equal to log of 64.5 divided by 5.4. All I'm doing now is evaluating the right hand side, so log of x is equal to 0.3351. I'm going to take anti-logarithms here. I've shown how to use a definition, but all you need to do on your calculator is do shift and the LOG key of the 0.3351, and you will get the answer of x is equal to 2.163. Exercise 1i continued here, part 2. We're given that 3 to the power of x minus 1 is equal to 4 to the power of 3x plus 2. We've got to find x. Again, our solution, we're going to take logs of both sides of the equation. So left hand side log of 3 to the power of x minus 1 is equal to, on the right hand side, log of 4 to the power of 3x plus 2. Applying my third law of logarithms here to both sides of the equation. On the left hand side I get x take away 1, and again notice it has to be in brackets. That's multiplied by log of 3. And on the right hand side 3x plus 2, again in brackets, multiplied by log of 4. Expanding the brackets here, I get on the left hand side x times log of 3, so that's x log of 3, take away 1 times log of 3, that's log of 3. And on the right hand side 3x times log 4, that's 3x log 4, plus in this case 2 times log 4. Collecting my like terms together, I get on the left hand side now x log of 3, and I've taken away from both sides the 3x log of 4. So all my x terms on the left hand side, and on the right hand side I get 2 log 4, in this case plus log of 3. So I'm bringing all my constant terms to the right hand side. On the next line I'm factorising on the x on the left hand side, x is a common factor, so inside the bracket I get log of 3, take away 3 times the log of 4. Right hand side remains the same. Simply now to find x, I rearrange the equation, so I get 2 log of 4 plus log of 3 divided by log of 3 minus log of 4. So I'm dividing both sides by, in brackets, log 3 take away 3 log 4. Doing the numbers on that, you'll find that x is equal to minus 1.265. And again, if you want to check the equation, you could put the value of x back into the original equation and check that the left hand side equals to the right hand side, which it does. Exercise 1I, part 3 here, we're given a descriptive question. A thermodynamic process follows the law T2 divided by T1 is equal to V1 divided by V2 to the power of K minus 1. We're given the temperatures T1 and T2 are 400 K and 200 K respectively, and also the volumes V1 and V2 are 0.1 meters cubed and 0.5 meters cubed respectively. We've got to find constant K. So given the equation, T2 divided by T1 is equal to V1 divided by V2 to the power of K minus 1. We know our values of T1, T2, V1 and V2. So I'm going to put those into the equation. On the left hand side I get my T2, which is 200, over T1, which is 400, and on the right hand side I get my value of V1, which is 0.1, over V2, which is 0.5. We're trying to find the K, which is the index. So I simplify my numbers first of all on the next line. So 200 divided by 400, 0.5, 0.1 divided by 0.5, 0.2 to the power of K minus 1. Just simplify to decimals there. I now take logarithms of both sides of the equation. So left hand side, log of 0.5 is log of the 0.2 to the power of K minus 1. And then apply my third law of logarithms to the right hand side. I get K times 1, notice it's in the bracket, multiplied by the log of 0.2. Simply rearrange the equation now to make K minus 1 the subject. I divide both sides by log of 0.2, so log of 0.5 divided by log of 0.2. Simply then rearranging the equation, K is equal to 0.431, add the 1, as I'm adding 1 to both sides, to give me 1.431. I would encourage you to attempt some tutorial questions here on Indicial equations, questions 1 to 8 given here, and the answers are shown in the box below. Questions 9 and questions 10 are descriptive questions. Again, the answers are shown here on the right hand side. The bibliography is also shown for your reference. I hope this has been helpful to you. Thank you for viewing.